Demeter, their song that fits my wife.
गुड इवनिंग एवरीवन. हेलो एवरीवन. बताइए आवाज एम आई ऑडिबल? एम आई ऑडिबल टू यू? Okay. Let's hope everything is fine. Very good evening, everyone. I welcome all of you to this session where we are going to discuss binary search tree. Okay, that is the topic, that is the agenda. Binary search tree. Okay, so I'll tell you two things, two interesting property. I'm going to explain. Yesterday we have done a very interesting topic which was Q. Okay, which was Q, and we have seen NQ and DQ. And we have seen some question related with configuration or let's say stack plus queue problem. Okay, we have seen stack plus queue problem. Very good evening everyone, one more time. Okay. Now we are going to see binary search tree. Okay, binary search tree. We'll see construction of binary search tree, insertion in binary search tree, we'll also do the search operation. We'll also see the traversal of the binary search tree. The traversal is the topic which is very interesting. Traversal of binary search tree, BST. Yeah? So this is my agenda. 3 topics I want to cover. I don't think so. I'm looking stylish. Basically, I'm exhausted, very much exhausted today for no reason. Okay, so let us begin. Now to begin with binary search tree, what is exactly a binary search tree? Okay, so BST, binary search tree, is a tree. Binary search tree is a tree in which all the element, okay, all the element in the left subtree okay, binary search tree in which, in binary search tree is a tree in which for each node, for each node, the key value in left is lesser than for each node, lesser than the key value of parent. And obviously I should not write, but yes, okay, but yes, the key value for each node, the key value at right is greater than the key value at parent. Now, this definition assumes keys are distinct. Okay. Chalo, I'll not go directly into the time complexity, but this definition is for the distinct keys. Distinct keys. And this is important because distinct means no keys are similar. Okay, no keys are similar. This definition is for that. Repetition is not allowed. Unique keys are there. But now if you say that what about sir if the equal keys are present, then for a given node equal keys we put into either in the left or right. Okay, we make a convention that if the equal keys are there, then it may go to the left one convention or go to the right another convention. But this definition is for the distinct keys. Okay, now so now the first part here in this case is suppose we insert the following keys into the binary search tree. This is the first thing that happens, and the first question I will ask based on this only. So listen to me very carefully. Now we are inserting the following keys into a binary search tree and we start with the construction process. Now obviously if you know the first element will be the root element. This is root. Okay. Understand the first element is a root always. So now the first element inserted is 14. Now let the key comes 12. Now we'll compare. Okay, we'll compare that it is lesser or greater. It is lesser, then it will go to the next empty position and it will be settled here. 23 is greater than 14. 23 will go over here. Next is 10. See the comparison. 14, 10 is lesser. 10 is lesser than 12 also. So now here in this case, this will go to the 10. 27, compare with 14 greater, compare with 23 greater, empty space, you put it over here. 20, now see, greater, lesser, greater than 14, lesser than 23, it is empty here, so now we'll put 20. 44, so greater, 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 empty position, fill. 5, lesser, 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 so 5. Okay. 2, okay, 2. So number of keys that has been inserted here in this case is 2. So lesser, 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 lesser. So now lesser, that is 2. Then is 6, lesser, 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 greater. 6 is lesser, 6 is lesser, 6 is lesser, this is greater. So 6 will come down into this position. Okay. Yes, comparison start from the root node. Okay, comparison start from the root node. If it is an empty tree, no comparison is needed. So this is the tree is been constructed by using binary search tree. Each element is been compared against starting from the root. It doesn't matter. Now if you look at the definition, for each node left subtree, this should be true. It's not about I can arrange this subtree in any order. No, for each node, the left one should be lesser and the right one should be greater. For this, left one should be lesser, right one nothing is there. For 10, left one should be lesser and right again nothing. For 5, lesser is 2 and for 6, greater. Okay. So for each key, for each node, this should be true that the element in the left subtree will be lesser than the key value of the parent, and obviously if it is lesser, the right side I don't need to say, it implies yes, it can be greater. This is the first construction of our binary search tree. This is how we construct the binary search tree. Okay. Now I hope that the idea of this is clear. Let's test this understanding that are you able to figure it out, the understanding. With this understanding, are you able to construct a binary search tree? Okay. So now let's start with this. Create a binary search tree and tell me the number of leaves into this. How many leaves are there? Okay. Shout out for those who answer it correctly. Okay. Let's start. Create a binary search tree among this. Let's discuss 1, 2, 3 interesting question related with this. Create a BST and count the number of leaves. Or if I want to, test your speed and accuracy, then I will say that find the sum of the leaf node. I'll say find the sum of the leaf node. Six. Okay. I guess there are 7 nodes. Are there 6 leaf? Are you sure? A little bit on the higher side, I guess. Number of leaves, it seems it is in higher side. How many leaf? Very simple question. How many leaf nodes are there? All 6? Let's say, just recheck. I don't know the answer, so I'll calculate anyway. No, I'm not saying sum of the leaf node. I'm saying just number of leaf node. Fair enough? Huh? How much time more you will take for this simple question? Now 40, so 40 will become the root. 40 is the root. 20 is lesser, so 20 will settle here. 60 is greater, so 60 will settle over here. 50 is again greater and then lesser. Greater here, lesser here, so 50 will come down to this. 30 is again lesser and greater, lesser and greater. So this is lesser, this is greater, so that will become in this case is 30. 10 lesser and lesser here, so it will come down to this 10. Next is 70, so in this case the 70 is greater here, it is empty, so now it is 70. Okay, so very simple. Don't get confused unnecessarily. Do not get confused unnecessarily. The number of leaves in this case is number of leaves is equal to 4. Okay, there are 4 leaves are there. Now this tree is having height of 2. Okay, so this root is at height 0. Okay, always root is at height 0. And what is height? Height is the number of edges, maximum number of edges, maximum number of edges from root to leaf path, root to leaf path, maximum number of edges. Okay, so the maximum number of edges is 2 only. Balanced, so in this case this is having height 2. Okay, height is 2. Now so let's go down to here in this another question from this construction part and find the height of the tree. Find the height of this tree. If you insert the following keys into the empty binary search tree one after another and following keys in BST, keys in binary search tree, binary search tree. Okay, so for BST if I insert one of the another, so tell me the height of the tree. Root is at height 0. What is height? So height is the maximum number of edges in leaf to root path, maximum. The term is maximum. Okay, so tell me the height. Height is 4. Great. So now the first one is origins, and then 𝐂𝐚𝐭𝐜𝐡, and then Ritu, and then Nishu, and then again one more time. Okay, great. So height is 4. Okay, let's construct. So 83. Okay, 83. 60, so that is lesser. 90, so that is greater. 45 is lesser. 97 is greater. 100, it is greater. Okay, now 94, so here it is greater, here it is greater, here it is lesser, so 94. Then comes 55, so here it is lesser, here it is lesser, here it is greater, so this is 55 for you. Then comes 65, so here lesser, here greater, so 65. Next is 40, so lesser, 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 so next is 40, and then 23, so lesser, 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 and 23. Okay, now this is 23. A leaf concept. Leaf is a node which is not having any children. Okay, so anything that is leaf means this is the end part. So all external nodes are leaf. All external nodes are leaf. External nodes are leaf. What is the definition? Node with no children. Node with no children. Node with no children. Okay, so 1, 2, 3, 4. So 4 is the answer here in this cases. Okay, now let's say number of comparisons. Let's talk about that, how many comparisons we do for construction of the tree. Okay, how many comparison we do for the number of tree. Like in this case, let me give you the hint here before I go to the question. Comparisons, number of comparisons, and this is very important term, comparison. Whenever we talk about complexities, complexity, when we talk about number of comparison is very important. 5, where is you are getting 5? 1, 2, 3, 4. Maximum number of ages. Okay, so 1 age, 2 age, 3 age, and 4. This side 1, 2, 3, only 3. So maximum number of ages here in this case is 4. Am I clear that answer is 4? And the height, idea of the height, I am not saying number of leaves, I am saying height of the tree. How many leaves? So 1, 2, 3, 4, and 5. There are 5 leaves. 5 leaves are there. Okay, there are 5 leaves are there. Okay, let's a little bit. Leaf node is 5. 1, 2, 3, 4, 5. Okay. Now, so now when I inserted 83, okay, so here in this case no comparison required. But when I inserted 60, I have to compare with this. Like I have compared 60 is lesser than 83, and then I inserted the value on the left. So for 60 I need one comparison. Okay, one comparison. Now similarly when I inserted 90, okay, 90, so I need to compare with 83. How I know that it will go to the right? So 83 is lesser than 90, or 90 is greater than 83, it will go to the 90. So this is one comparison. Okay, one comparison. So when I inserted 83, no comparison. When I inserted 60, I compared with 83, then I settled into the left. Then I inserted 90, and then it is settled in the right. So this is how the tree is constructed. Okay, this is how the tree is constructed. My next question to you is very, very simple. Okay, very, very simple. That constructed with the following keys in the order. Assume each comparison is counted whether key is compared with the node key during the insertion. Okay, that each comparison is counted. Every comparison we are counting. What is the total number of comparison in construction of this binary search tree. Okay, what is the total number of comparison in construction of the binary search tree? And let me add one more thing, root is not compared, root is having zero comparison. Okay, zero comparison. So can you tell me that how many comparison required? Okay, how many comparison required? Let's not go into the terminology. I need very few terminology right now, and I want you to understand the binary search tree proper manner. And in that regard, I am explaining you few concepts. If you are missing out something, let me know. I will clarify. Okay, I will clarify. Now, root is no comparison. Can you tell me how many comparisons are required if I insert the following keys in the given order? If I insert the following keys in the given order, how many comparison required? Is it A, B, C, D? 13, 15, 17 and 19. Can you answer this question, which is about how many comparison required? Again a challenge for you. Simple challenge. Simple challenge. Simple. It's not very complicated, but it required some amount of computation, and for that you are, I think, capable of doing this. You are capable of doing this. I'm not making anything very complicated. Simple. Nishu is promoting NIT Allahabad. How is NIT Allahabad, Nishu? What was your experience in NIT Allahabad? Oh, don't think, do not think. Do not think. You have to be sure about things. There is a problem because the whole point is, confidence and no confusion. So I just want you to be answer it properly. I think that is not a correct term. I think yesterday also you are trying to guess something. Ronins. Let's start. Okay. Very simple, and let's construct the tree. Let's start with 45. Then I insert the value 25. 65 greater. Sir, you are not counting. I will count. Don't worry. I will count. Do not worry. Okay. Then comes 15. Fine. Then comes 35. So here it is lesser and here it is greater. So 35. Then comes 55. So here it is greater, here it is lesser. So that is 55. Next is 75. So now 75 will settle over here. And next one is 30. Okay, next one is 30. MTech is average. Okay. 30. So 30 will go where? 30 will be lesser, greater, lesser. So 30 will settle here. 4. Let me count it now. Let me say the answer. I say root does not require any comparison. So I'll write here 0. Okay. Now when you insert the value 25, you have to compare with 45. Then you come to this particular height 1 or depth 1. Okay. So all the node is in the depth 1 or let's say level 1 required one comparison. Okay. Because 25 will be compared with 45. And 25 will be again compared, 65 will also compared. So all the nodes in this level 0, level 1, okay, another terminology, all the nodes of the same depth, okay, or same height, let's say, if you are not, unless height is not a proper term, but you can say right now. Here when you come this level, 15 will be compared with 45 and 25, 35 will be also compared with both element, 55 compared with 45, 65 and 75 will be also compared with 45 and 65. So two comparisons. So every element at this level, which is level 1, this is level 2, okay, level 2 required two comparison. Okay. So first level no comparison. There are two elements at level 1 required one comparison. There are 4 elements, 1, 2, 3, 4 required 2 comparison, and when you come to the next level, level 3, obviously this required 1, 2, 3 comparisons. So they required 3 comparisons, correct? So now for 30 it will be 1 element and that required 3 comparison, and that goes to 10 plus 3, that is equal to 30. Okay, so total number of comparison required here in this case is 13. 13 comparisons will be required to construct this tree. Okay, construct this tree. Now if I say that if I insert 1 to n, answer it properly. If I am inserting the value 1, 2, 3, 4 up to n in the given order, in the given order in empty binary search tree, natural number, then number of comparison required, I am giving you option, number of comparison required. So answer A, is it n? Answer B, is it n square? Answer C, is it n into n plus 1 divided by 2? Answer D, is it n into n minus 1 divided by 2? Okay, this question. How many comparisons are required if I insert a given element in the given order in empty binary search tree? How many comparisons required? Done? We have to remove root. Why? So let's start. So now the first element, 1, no comparison, as we are making this convention that first element no comparison. Second will come, then second element will have 1 comparison, 2 greater. When 3 will come, it will have inserted here and it will have 2 comparison. When 4 will come, it will compare with 1, 2, 3 and then 4, so it will require 3 comparison. And similarly when n will come, you can see there is a 1 lesser comparison, so number of comparison will be n minus 1. Okay, so how many comparison, how we count it? So we'll add the number of comparison, 1 plus 2 plus 3 plus 4 up to how many comparison? N minus 1 comparison, and that is equal to n into n minus 1 divided by 2. Okay, this is the worst case BST construction time. Construction, heavy word, time complexity. Tree construction, time complexity, and that will be, what is the highest power of n square? So that is order of n square. So worst case tree construction worst case tree construction, binary search tree, if you construct, it will take n square time. Okay, why it is n square, sir? Where n square is coming? Where are other terms? So if you open this will come as 1 by 2. It will become n square minus n. Okay, 1 by 2 n square minus n. So the largest power we consider, we ignore the constant, we ignore the lesser terms. So we ignore constant and the lesser terms, and that is the reason that we only consider order is the worst case maximum time, and n square because n largest power is. Great, very nice. So this is about BST construction. Now let me tell you the insertion sequence, some insertion sequence. Okay, now when I constructed a BST, first you understand the simple thing. After that, now suppose your BST is 1, 2, 3, okay, 1, okay, sorry, 2, 1, 3, and then 4. Suppose this is 4. Okay, let me first make you understand what I am asking. Question is that how many ways, how many insertion sequence, okay, how many insertion sequence of keys, key, this is not the order, 1, 2, 3, 4 will result in the given BST, the given BST. First you understand the question before you answer it. Means the key is given to you 1, 2, 3, 4. Okay, my question is that how many ways I can create an insertion sequence so that this tree will be resultant. Like I can give you one insertion sequence as 2, 1, 3, 4. This is one insertion sequence. Now tell me how many ways I can have insertion sequence that will result in this simple binary search tree. How many ways? Are you getting my question? What I'm trying to ask? Are you getting my point? Are you getting my question here, that what is the insertion sequence and how many such sequences are possible? Yeah, then answer. Factorial 4 is not possible, Babu. Factorial 4, Ritu. Factorial 4 is not correct, because factorial 4 can also start with 4, and if you insert the first value is 4, then 4 will become the root, and this will not result in that tree. This will not result in that. Why factorial 4 is not correct? So for factorial 4 this is also possible, 4, 3, 2, 1. But if this is your insertion sequence, then it will be 4, then 3, then 2, and then 1. So not possible. Not possible. 4, 3, 2, 1. So factorial 4 is not the correct answer. More than 1. More than 1. मतलब total 4. Total 4. Ronnie Gen Z. Ronnie Gen Z. No, you cannot have, tree is fixed, tree is fixed, tree is fixed, you cannot take 3 as a root, because if you take any sequence that start with 3, okay, any sequence that start with 3, okay, any sequence that will start with a 3, then 3 will become the root. So you cannot take, simple reason, you cannot take. Not possible? Yes or no? Are you getting? I'll write all the sequence and I'll generate that also. I'll write all the sequence and I will generate that tree. Yes. So first position. Okay, if there are, let's put some mathematics into this. Mathematics I know you don't like, but we have to do this. The first element, there are 4 positions are there. 4 positions are there. Okay, and this 4 position, 2 is the first one. Okay, 2 is the first one. 2 is the first one. Okay, let me write all the sequence. Now tell me left and right, just say like 2 1 3 4. Just tell me one thing, can I change my sequence 3 4 to 4 3? Answer my question. You will be getting answer here and I'll write all the 4 sequence. Can I change my sequence 3 4 to 4 3? Can I change my sequence 3 4 to 4 3? Can 4 come before 3? Is it possible that if 4 is coming before 3, then same tree will be generated? So 4 cannot, no, right? No, it is not possible that 4 will come before 3. So 3 will come before 4. 3 should come before 4, right? It is not possible. So if it is not possible, then here in this, I can write 3, 4 and then 1, right? I can write 2, 2 is the first one. I can write this 3, I can write 3 and 4 over here and 1 I can insert in the middle. Why I can insert in the middle? Because 1 will go to the left and 3 and 4 will go to the right. Why, right? Another sequence is 2. What is the next position? 3 4, 3 4 and 3 and 4. Okay, 1 can be inserted over here. That is my sequence. Only 3 sequences are possible that will result in this particular tree, and in this case if you take the first one, you take any one. Now problem is same tree will resultant. So 2 3 4 and then 1. 2 3 4 1. What about this, sir? So let's insert 2, then 3, then 1 go to the left side and then 4. Next, this one 2 1 3 4. So first is 2. Okay, first is 2, then 1, then 3 and then 4. Okay, see, all are different. 2 3 4 1, 2 3 1 4, 2 1 3 4. Okay. Each question is different. You have to find the positions. So basically you have to select 2 position out of the 3 positions. So I can devise a formula, but that is not a generalized formula. Okay, so only 3 sequences are possible. Okay, only 3 sequences are possible, and for each such sequence we cannot derive a generalized formula because there is a dependency and there is a selection problem. Okay, now based on this, tree is given to you, sequence is given to you. Okay, tree given and sequence given. You have to tell me that which sequence will result in this tree. Okay, I am not asking how many, I am not asking how many, I am asking which sequence 1 2 3 4 will result in this particular tree. More than one answer is correct. If more than one answer is correct, we call that question as MSQ, multiple select question. Hmm. Very nice. Very good. So, 5. Okay. Let's see whether, let's keep on marking it. We are done. Like 5. Okay. Correct. 3. Correct. 4. 3 and 4. Fine. 9. Correct. 12. So 9 after that 12. Correct. 7. Correct. Then 8. Correct. Then 6 and then 20. A is correct. Okay. A is correct. Now, B, what about B? So B is 5, cut, 9. So 5 after 9 valid, 3 is valid. Now in this 7, 9 is done, so 7 valid, 6, 5, 9, 7, 6 done, yes. 8, 8, 8, 7 is done to 8 is valid, 4 valid, 3 is done, 3 is already cut, 4 is valid, 12, 9 is done, 12 is valid, and 20. B is also correct, A and B both are correct. Okay. C, 5, cut, 9, okay, 5 after 9, good, 7, yes, 3, okay, 5 and then 3, 8, yes, 12, yes, 6, yes, 4, yes, and then 20, yes. Last one, okay, last one. So what is this? 5, correct, 9, okay, see, 3, okay. Now you see that after that it is inserting 6. Now 6 cannot be inserted until 7 comes. 7 is not cut, but now I am inserting 6. So in this case it is not possible. Okay, it is not possible. So correct answer is what? A, B and C. All three are correct. A, B and C. All the three are correct here. Okay, that is a example of MSQ question of very basic level. In examination it is more brutal, more you can say cruel. Cruel type of question is MSQ. Okay, MSQ is very cruel type of question. Now can you guess answer for the same tree? About this same tree but false. Dependency is there, like 3 4 I cannot write 4 3. That means the dependency was that this, when I say 3 4, okay, there is a dependency for this tree. What is the dependency? That 3 must be inserted first followed by 4. 3 must be inserted first followed by 4. So can you answer this, that is it satisfying the dependency? Multiple answer may be correct, may be correct. So you search every option, you find, see every option over here. Okay, see every option over here. B and C false. Are you sure about this? Okay. Now 5 is inserted as the first, definitely 5 should be inserted as the first element. 6 and 8 must be inserted after 5, 9 and 7. Okay. So now it is saying that 6 and 8 must be inserted after 5, 9 and 7. So you look at here 5, 9 and then 7. Then if you insert 6 and 7, okay, 6 and 7, then 6 will go to the left or and 8 will go to the right. Now if you do not, if these are not inserted, suppose let's say 9 is not inserted and you violate this, that 6 you insert 6, anything you violate, 5, 9 and 7. So 6 will come here and it will become the root, it will violate this. So 6 and 8 must be inserted after 5, 9 and 7. So this is also true, this is also true. Next, 12 must be inserted after 5, 9 and 7. 5, 9 and 7. After that you insert 12. Now if I say 5, 9 and 7, okay, after 5, 9 and 7, I can get a tree, the same resultant if I insert 5, 9, 12 and then 7. Any problem in that? If I change the sequence, if I do not follow this order, that 12 must be inserted after 5, 9 and 7. If I insert the value 12 before 7, will it be there any issue? So now look at this side, 5, 9, 12, and so I am getting the same tree. Okay, I am getting the same tree, and this means this statement is a false statement. C is false. It is not mandatory that 12 comes after 5, 9 and 7. If it say only 5 and 7, if it say only 5 and 7, okay, 5 and 9, sorry, if I say only 5 and 9, I agree on that. Okay, I agree on that. If I say 5 and 9, then I agree. Otherwise, no, this is not false. This is not true. It is false. Okay. Now it says that the last element should be any sequence you draw. Any sequence you draw, the last sequence should be 4 or 6 or 8 and 20. Now the idea here in this case is, will the last number will be a leaf node or not? The last element that you are inserting will settle as a leaf or not? Question to you. Yeah, the last 3 cannot be the last, because if you 3 is the last, after that 4 must be there, right? So it has to be a leaf node. The last element, whatever sequence you design, we can go back to this question. You see, all the leaves are this. Okay, you take out 4 and you exchange 4 and 20. Okay, it should settle as a leaf. You exchange like this. Suppose I give you 3 and I write here this sequence. I take out this 4, which is also a leaf, and instead that okay, 20 dependent on what? 9 and 12. So I write the sequence 5, 3, 5, 3, 4 I take out, 9, 12, 7, 8, 6, 20 and 4. I change the sequence. Okay, I change the sequence. I take out 4 from here, and I kept all the other sequence same, and after that 20. Look at here, 5, 3, 9, 12, 7, 8, 6, 20 and then 4. Okay, so the last element should be a leaf node. So in that way this statement is also correct. Okay, so now multiple answer may be correct, and this statement is also true. The only thing that is false here is only C option. Am I clear with all the option over here? Am I clear with this idea that 5 is the first element is true, 6 and 8 must be inserted after 5, 9, 7, true. Okay, fine. So answer here in this case is C. But if you have solved 80% of your PYQs, you have done a very good job. Huh? The second job should be that now if the 80% PYQs are solved from which topic? All the topic, then you are ready for the test series. Go for the test series now, and you mark all the difficult problems. Huh? You mark all the difficult problems so that you can revisit them. Please understand, mark all the difficult problems so that later you can revisit them. Okay, so that is my suggestion for you, and on that note we'll stop the today's session. That is the binary search tree from very basic perspective. Okay, very basic perspective from my side. This class ends today. Tomorrow I will come and again give you more insight about another topic, which is binary heap. Okay, binary, this is the topic I am going to touch tomorrow. Binary heap, everything basic from nothing perspective. Okay, binary heap will start. I believe that the timing will not change, so 6:30 p.m. Thank you all of you. Thanks for joining, and I'll see you tomorrow. Traversal will not do today. Maybe we'll try to cover tomorrow. Okay, traversal. If we get time, we'll try to cover tomorrow. Okay. Thank you all of you. I need to go to the another session. Okay. YT session. Okay. Chalo.